Picture yourself assembling an incredibly complex jigsaw puzzle, one with trillions of pieces. You've spent decades on it, and the picture is almost complete. You understand the basic rules, you see the overall logic. Then, right at the very end, you find a piece that doesn't fit anywhere. It's from a different set, a different shape, a different color. What does this mean? Was all your work for nothing? Are the rules you derived fundamentally wrong? This is precisely the situation astronomers around the world find themselves in today. The tool that handed them this impossible piece was the James Webb Space Telescope. It looked into the universe's earliest epochs and saw something that, according to all our current theories, simply shouldn't exist: a giant, fully mature galaxy that appeared almost immediately after the Big Bang. In this deep dive lecture, we will travel 13.5 billion years into the past. We'll explore why this discovery casts doubt on the fundamental cornerstones of cosmology and what bold new ideas scientists are developing to explain this paradox. Get ready as we begin our descent into the mystery of the impossible galaxy. Before we get to the core of the discovery, let's set the scene and familiarize ourselves with our main instrument. The protagonist of our story is the James Webb Space Telescope, or simply Webb. It's more than just a telescope, it is a true time machine. When we look up at the stars at night, we are seeing light that took years, sometimes thousands of years, to reach us. We are looking at the past. Webb, however, was designed to see the past not by thousands but by billions of years. It operates in the infrared spectrum. Why is this crucial? Because the universe is expanding. The farther an object is, the faster it recedes from us. Due to this effect, known as redshift, the light from the most distant, earliest galaxies is stretched, shifting it from the visible spectrum into the infrared. With its enormous 6.5-meter mirror coated in a delicate layer of gold, Webb is able to capture this ancient, faint light. It was launched into space to answer fundamental questions. What did the very first stars and galaxies look like? How did they coalesce from the primordial chaos following the Big Bang? Scientists had a very neat, well-defined framework for this, the so-called Standard Model of Cosmology. It posited that galaxies grew slowly, gradually. Small clumps of matter merged into larger ones, which then merged into even larger ones. This was supposed to be a long, unhurried process, spanning hundreds of millions, or even billions, of years. Everything matched up. Computer simulations painted exactly this picture. Until Webb pointed its gaze into the void and saw a monster. So, let's begin our deep dive with the instrument itself, the tool that has allowed us to peer into the depths of the cosmic void farther than ever before. The James Webb Space Telescope is a marvel of engineering, the culmination of decades of work by thousands of scientists, engineers, and technicians worldwide. It is often called the successor to Hubble, but that's not quite accurate. It is better described as its technological and scientific heir, one that views the universe in a radically different light. Webb's primary mirror is its most recognizable feature. It is comprised of 18 perfect hexagonal segments that collectively form a single, reflective surface 6.5 meters in diameter. For comparison, the Hubble mirror was only 2.4 meters across. Webb has roughly 6 times the light collecting area, which allows it to observe much fainter and more distant objects. Each of these segments is made of beryllium, an incredibly lightweight and strong metal that excels at maintaining its shape at extremely low temperatures, and the temperatures out there are truly extreme. To capture the faint infrared light from the very first galaxies, the telescope itself must be colder than any freezer on Earth. Its operational temperature is about -223 degrees Celsius. To achieve this coldness, Webb is equipped with a gigantic 5-layer sun shield about the size of a tennis court. Each layer of this shield is thinner than a human hair. It reflects solar heat, allowing the telescope to cool down to the necessary temperature. But why are the mirrors coated in gold? It's not about luxury. Gold is the perfect material for reflecting infrared light. The thin layer of gold applied to the mirrors ensures that 99% of the incident infrared radiation is reflected, directing it precisely into the telescope's scientific instruments. This complex mechanism was folded up like origami and packed into the Ariane 5 rocket for its journey 1.5 million kilometers from Earth to the Lagrange point L2. At this location, the gravitational forces of the Earth and the Sun balance each other out, allowing the telescope to maintain a stable orbit, constantly staying in our planet's shadow. It is the ideal location for observation, protected from the heat and light contamination of Earth. It is from this cold, dark vantage point that Webb began its vigil, gazing into the dawn of time to find what will fundamentally change our understanding of the cosmos. Now that we understand the power of the instrument we possess, let's turn our attention to the theory it was intended to confirm. This theory is known as the Standard Cosmological Model, or Lambda CDM. It's not just a hypothesis. It is the cornerstone of modern cosmology, built upon decades of observations and theoretical calculations. It describes the universe from the very first fractions of a second of its existence right up to the present day. At the heart of the model is the concept of the Big Bang, the moment roughly 13.8 billion years ago when the entire universe was compressed into an unimaginably hot and dense point, a singularity. From that instant, it began to expand and cool. The Lambda CDM model tells us what our universe is actually made of, and its composition is rather strange. The normal matter, the stuff that makes up us, the planets and the stars, accounts for only about 5%. Another 27% is the mysterious dark matter. We can't see it, it doesn't emit or reflect light, but we know it's there because of its gravitational influence on visible matter. It acts as a kind of cosmic glue that holds galaxies together. The remaining 68% is dark energy, an even more puzzling substance believed to be responsible for the accelerated expansion of the universe. The CDM in the model's name stands for cold dark matter. Cold in this context means that its particles move slowly. This distinction is crucial for understanding how galaxies were formed. According to this model, immediately after the Big Bang, dark matter began to clump together under its own gravity, forming dense structures called halos. These halos acted as gravitational wells, pulling in the ordinary matter, primarily hydrogen and helium. As gas fell into these wells, it compressed, heated up, and eventually began to form the very first stars. This process was hierarchical. Initially, small halos formed, igniting the first stars. Then these small structures merged with each other, building progressively larger halos and, consequently, bigger protogalaxies. It's analogous to how small droplets of water on a pane of glass merge into rivulets, and rivulets flow into larger streams. The model predicted that this process had to be very slow. To form a large, massive galaxy like our own Milky Way, billions of years of mergers and absorption were required. The first few 100 million years after the Big Bang should have been a period of small, faint, nascent galaxies. The universe was expected to light up slowly and gradually. This picture was elegant, logical, and supported by numerous observations, such as the cosmic microwave background. It became the accepted standard. Scientists expected that Webb would simply add detail to this picture, showing us these young galaxies in the process of their slow growth. But the reality turned out to be far more shocking. And so, the moment of truth arrived. After months spent calibrating and fine-tuning its instruments, Webb commenced its scientific mission. It turned its golden eye toward patches of the sky that had appeared completely blank, even to the Hubble telescope. These projects, known as deep fields, demand hundreds of hours of exposure time. The telescope stares fixedly at a single point, gathering photon after photon, the faint light emanating from the most distant reaches of the cosmos. Among the thousands of tiny pinpricks of light, each one an entire galaxy, astronomers began noticing something peculiar. They found several candidate galaxies that were both intensely bright and unusually red. The red color, of course, signals extreme distance and, consequently, a very early epoch in cosmic history. Analyzing this light, a process called spectrometry, allowed them to determine the redshift. This parameter, designated by the letter Z, indicates how much the light's wavelength has been stretched due to the expansion of the universe. The higher the Z value, the farther away and older the object is. For some of these galaxies, the redshift Z was greater than 10, and in a few cases it approached 13. This means we are viewing them as they existed only 300 to 500 million years after the Big Bang. That in itself was an incredible observational feat to peer back so far. But the true shock came when they measured their mass. Based on their brightness and color, scientists estimated the stellar content of these galaxies, and the numbers were staggering. One such galaxy, designated JWST, was estimated to already hold the equivalent of 1 billion solar masses worth of stars. Other candidates proved to be even more massive. For context, it took our own Milky Way nearly 13 billion years to accumulate its current mass. Yet these infant galaxies were already true behemoths in the early universe. They weren't just chaotic clumps of primordial stars. They were already well-formed, structured systems. It was the equivalent of walking into a nursery and finding a fully grown adult among the infants. This simply defied conventional wisdom. The Standard Cosmological Model, as we know, predicted slow, gradual growth. 300 or 400 million years was not supposed to be enough time to collect that much gas in one spot and convert it into such a colossal number of stars. The universe should still have been in its toddler phase, filled with tiny proto-galaxies. Instead, Webb revealed teenagers that had reached incredible sizes in record time. Scientists checked the data repeatedly. Was there an error in the calculation? Were they incorrectly estimating mass based on brightness? Or perhaps these weren't galaxies at all, but rather something else entirely, like quasars, supermassive black holes aggressively feeding on matter? But subsequent observations, including detailed spectroscopic analysis, confirmed the initial findings. These truly were galaxies, and they were indisputably massive, anomalously so, for their age. The puzzle pieces simply didn't fit, and this implied that either we were critically missing certain details about the early universe, or the entire cosmic framework we had spent decades constructing might be fundamentally flawed. Let's now dive deep into the core problem. Why was it so incredibly difficult for a galaxy to rapidly grow to giant size in the early universe? This issue is multifaceted, challenging the very bedrock of how we understand cosmic evolution. Picture the universe just 300 million years after the Big Bang. It was incredibly young and largely unstructured. Matter density was higher than it is today, but it was still quite uniformly distributed, with only tiny fluctuations. According to the Lambda CDM model, the process of galaxy formation begins with the gravitational collapse of dark matter halos. These halos serve as the scaffolding upon which normal matter then accumulates. The first major constraint is the growth rate of the dark matter halos themselves. Even though dark matter doesn't experience pressure and readily collapses under gravity, it still requires significant time to assemble into structures massive enough to anchor a whole galaxy. Computer simulations based on our best theories indicate that only relatively small halos should have formed in the first few 100 million years. Massive halos, the kind needed to host a giant galaxy, simply shouldn't have existed in any significant number by that point. This is a fundamental speed limit. Our second limitation is the efficiency of star formation itself. Even if we assume a massive dark matter halo miraculously formed quickly, gas would have rushed in. As this gas falls into the gravitational well, it heats up to millions of degrees. For stars to form, the gas must first cool down and condense. In the modern cosmos, this cooling is accelerated by heavy elements, or metals, as astronomers refer to them. These elements are excellent at radiating heat away. However, the early universe was nearly devoid of metals. The first stars were composed only of hydrogen and helium, and the surrounding gas was just as pure. Cooling this pristine gas is a much slower, much harder process. The third constraint, and arguably the most critical, is stellar feedback. When the first massive stars ignite in a young galaxy, they have very short lives and explode spectacularly as supernovae. These explosions, coupled with the intense radiation from the stars themselves, create enormous pressure. They literally blow the surrounding gas out of the galaxy, halting any further star formation. This self-regulating mechanism should have constantly prevented young galaxies from rapidly accumulating mass. They would have experienced a burst of activity, then shut down for long periods until they could gather gas again. In essence, for Webb to observe these massive galaxies, the early universe must have somehow violated all these theoretical constraints simultaneously. We would need the dark matter halos to have grown faster than predicted. We would need the gas to cool down and convert into stars with almost 100% efficiency, which is physically impossible, and we would need the feedback from the first stars to somehow be non-existent or much weaker than we currently believe. Taken together, this is what creates the paradox of the impossible galaxy. It doesn't just challenge one single assumption, it throws the entire hypothesized sequence of galactic birth into question. This forces scientists to ask, are we overlooking a completely new, unknown physical process that dominated the conditions of the early universe? Faced with such a stunning paradox, the scientific community didn't give up. Instead, it doubled down, generating new, and sometimes very bold, ideas. If the old rules don't work, we clearly need to find new ones. Let's look at the first group of hypotheses. These attempts to solve the problem without scrapping the entire cosmological model, but rather by modifying specific elements within it. Specifically, these hypotheses concern the very first stars. The Standard Model assumed that the first generation of stars, known as population stars, were extremely massive, perhaps hundreds of times the mass of the Sun. But what if they were even more extreme? This led to the concept of supermassive population 3 stars. These are hypothetical objects whose mass could reach tens or even hundreds of thousands of solar masses. Such giants would be incredibly bright and hot, living for only a few million years. However, in their short lifespan, they could profoundly influence their surroundings. First, they could produce heavy elements much faster than normal stars, enriching the surrounding gas and accelerating its cooling for subsequent star generations. Second, upon death, these stars wouldn't just explode as standard supernovae, they could directly collapse into intermediate mass black holes, ranging from hundreds to thousands of solar masses. These black holes would act as seeds that could then rapidly grow by consuming the surrounding gas. This brings us to another closely related idea, direct collapse black holes. This theory posits that in certain exceptionally dense regions of the early universe, massive gas clouds could collapse under their own weight directly into a massive black hole, bypassing the stellar phase entirely. Such direct collapse black holes could potentially be tens of thousands of times the mass of the Sun right from birth. The presence of such a massive black hole at the center of a protogalactic cloud would fundamentally change the picture. It would act as a powerful gravitational focus, drawing in gas far more efficiently than a dark matter halo alone. This could accelerate star formation in the surrounding disk, creating dense, bright galaxies in a very short timescale. Essentially, these theories change the initial conditions. Instead of starting from scratch and slowly building a galaxy, we begin with a ready-made massive seed, whether it's a supermassive star or a black hole. It's analogous to trying to grow a crystal. You can wait for it to slowly nucleate on its own, or you can drop a small seed crystal into the solution, accelerating growth dramatically. While these hypotheses look promising, they also face challenges. The conditions required to form supermassive stars or direct collapse black holes must be very specific and potentially rare. It remains unclear whether such processes could have occurred frequently enough to explain all the massive galaxies that Webb is finding. Nevertheless, this is one of the most active areas of research today. Scientists are developing new computer simulations to test whether these exotic scenarios could indeed lead to the appearance of impossible galaxies in the early universe. To continue solving the puzzles presented by the James Webb Telescope, we must turn our attention to another fundamental ingredient of our universe, dark matter. In the standard lambda-cold dark matter model, or lambda CDM, it is defined as cold. This implies that its hypothetical particles move slowly and interact only through gravity. This crucial property is what allows dark matter to efficiently form small, initial density fluctuations, which then merge into the massive structures we observe today. But what if dark matter isn't so cold after all? What if it possesses properties we haven't yet suspected? This leads us directly to alternative dark matter models. One prominent example is warm dark matter, WDM. In this scenario, dark matter particles have higher velocities. Because of this speed, they struggle to coalesce into small clumps. Their thermal motion prevents gravitational collapse on small scales. As a result, in a WDM universe, the first structures to form are not tiny halos, but immediately large elongated structures known as filaments. Gas then condenses inside these filaments to form galaxies. This top-down scenario, unlike the hierarchical bottom-up structure formation of lambda CDM, could potentially explain the rapid emergence of massive galaxies in the early universe. However, the warm dark matter model has its own difficulties. It struggles to explain the observed number of small, dwarf galaxies in the modern universe. If dark matter were warm, we would expect to see far fewer of them. A more exotic idea is self-interacting dark matter, SIDM. In this model, dark matter particles can interact with each other not just gravitationally, but through some other, currently unknown forces, much like ordinary particles collide. Such interactions could cause the central regions of dark matter, halos, to become much denser than predicted by the Standard Model. This, in turn, could accelerate the influx of gas into the center and trigger a violent burst of star formation. Finally, there is the concept of fuzzy, or hanaction, dark matter. This theory proposes that dark matter particles are actually extremely lightweight particles, axions, and behave more like waves than discrete particles. On cosmological scales, this can lead to structure formation that is drastically different from the predictions of the cold, dark matter model. All these alternatives remain purely theoretical constructs for now. While they might solve the mystery of early massive galaxies, they could introduce new problems in other areas of astrophysics. Crucially, each of these models makes unique predictions about how galaxies should be distributed, the specific shape of their halos, and so on. And this is where the James Webb Space Telescope steps back into the spotlight. Its detailed observations of the structure and dynamics of both early and nearby galaxies could provide the necessary clues to understand the true nature of dark matter. If the standard cold, dark matter model proves to be incorrect, it won't just be a minor correction, it will be a true revolution in our understanding of 85% of all matter in the universe. Up to this point, we've primarily examined hypotheses aiming to patch the existing cosmological model by tweaking its components, such as the properties of the first stars or the fundamental nature of dark matter. But what if the problem runs deeper? What if the very foundation, the lambda CDM model itself, requires not just refinement, but a radical overhaul? This path is the most extreme, forcing us to ask deeply uncomfortable questions about the fundamental laws of nature. One such idea challenges the constancy of dark energy. In the Standard Model, the density of dark energy described by the cosmological constant lambda is treated as fixed and unchanging over time. But what if dark energy behaved differently in the early universe? There are dynamic models of dark energy. For instance, in the very first epochs, its effect might have been attractive rather than repulsive. This could have accelerated the collapse of matter and the formation of the first structures. Alternatively, perhaps dark energy didn't emerge immediately, but rather arose later during the universe's evolution. Such changes in dark energy behavior would fundamentally rewrite the entire history of cosmic expansion, and consequently, the growth rate of galaxies. Another, even bolder hypothesis concerns gravity itself. We are used to treating Einstein's general relativity as an unassailable law. However, GR has primarily been tested within the confines of our own solar system and the modern universe. It's possible that on the largest cosmological scales, or under the extreme density conditions of the early universe, gravity doesn't operate exactly as we currently understand. There are alternative theories of gravity, such as modified Newtonian dynamics, or MOND, and its relativistic generalizations. These were initially proposed to explain galactic rotation curves without the need for dark matter. While these theories face numerous challenges, they highlight that our comprehension of gravity might be incomplete. If the gravitational interaction in the early universe was stronger than predicted by general relativity, this could significantly accelerate the formation of the first halos and galaxies. Finally, there are highly exotic cosmological models that move away from the idea of a singular Big Bang. For example, cyclic universe models, where our cosmos passes through an infinite sequence of expansions and contractions. In such scenarios, structure and matter might have survived the previous cycle, meaning the early universe wouldn't be as homogeneous as we currently assume. It might have already contained relics or seeds of supermassive black holes or dense clumps of matter, which then served as centers for the anomalously fast formation of galaxies. Of course, all of this currently borders on science fiction. Any change to fundamental constants or laws of nature must not only explain the Webb findings but also remain consistent with the enormous body of other astronomical observations we have accumulated. This is an incredibly difficult task. Nevertheless, the mere fact that scientists are seriously discussing such radical ideas underscores the severity of the challenge posed by these impossible galaxies. They compel us to rethink the very foundations of our cosmic framework and be ready for the possibility that the universe may be far stranger and more surprising than we have ever imagined. Let's step back from the high-level theories and look closely at the observational data. The critical question we need to ask is, how certain are we about what we are actually seeing? Is it possible that our methods for interpreting the data collected by Webb contain hidden errors or overlook crucial factors? This constant self-critique, this relentless re-examination of our own methods, is an absolutely essential part of scientific work. The core challenge lies in how we measure the mass of a distant galaxy. Obviously, we can't just put it on a scale. Instead, we measure its brightness across various light filters. We then construct a model designed to reproduce those observed colors and luminosity. Within this model, we input numerous assumptions: the age of the stellar population, its chemical composition, or metallicity, the amount of dust present, and how it absorbs light, and, most crucially, what's known as the initial mass function. The initial mass function, or IMF, is the distribution that describes how many stars of different masses are born during a single burst of star formation. For decades, astronomers have relied on standard IMFs derived from observations of nearby galaxies like the Milky Way. These standard functions tell us that for every massive star, many small dim stars are born, and it's these smaller stars that account for the galaxy's total mass. But what if this function was entirely different under the conditions of the early universe? Some theories suggest that in the pristine gas of the early universe, gas largely devoid of heavy elements, stars had to form predominantly as massive giants. Small stars like our Sun might not have been able to form at all. If this is true, the stellar populations in these early galaxies would be heavily skewed toward bright blue giants, and that means that if we apply our standard models, we could be vastly overestimating the total mass of the galaxy. The galaxy might appear extremely bright, not because it contains countless stars, but because the stars it does have are all massive giants, shining with the luminosity of thousands of ordinary stars combined. If we correct the initial mass function, the calculated mass of these impossible galaxies could drop by a factor of 10 or even 100. They would suddenly stop being so impossible. They would simply be extremely bright and active, but their overall mass would fit comfortably within the Standard Cosmological Model. Another factor is dust. Dust absorbs blue and ultraviolet light and re-emits it in the infrared, making the galaxy appear much redder. We try to account for this effect, but our dust models are based on modern galaxies. In the early universe, the properties of this cosmic dust might have been completely different. An error in estimating dust content can easily lead to a significant miscalculation of mass. Finally, there is the possibility that some of these objects are not ordinary galaxies at all. They might be so-called obscured quasars. A quasar is the active core of a galaxy, where a supermassive black hole is actively feeding on matter. This process generates so much energy that it can completely outshine the light from every star in the galaxy. If we look at such an object, we could easily mistake the light from the black hole's accretion disk for light coming from stars, leading to a wildly incorrect mass estimate. Webb and other telescopes are now actively working to resolve these uncertainties. Through spectroscopy, they can more precisely determine the chemical composition, age, and dynamics of these galaxies. This will allow us to refine their mass estimates and determine whether we truly face a crisis in cosmology or if we simply need to update the tools we use to weigh the universe. Let's take a quick detour from the mass puzzle and look at another surprising feature of early galaxies that the James Webb Space Telescope has uncovered: their shape and structure. According to the hierarchical model of galaxy formation, the first galaxies should have been small, lumpy, and chaotic. They were expected to look like disorganized blobs of stars and gas, constantly colliding and merging. Beautiful, ordered structures like spiral arms or flat disks were expected to appear much later, only after galaxies had accumulated significant mass and settled down. However, Webb showed us something entirely different. Among the very distant galaxies, those we see existing just 1 or 2 billion years after the Big Bang, it found an astonishing number of disk galaxies, galaxies possessing a clearly defined, flat, rotating structure, much like our own Milky Way or the Andromeda Galaxy. This poses yet another mystery. How could such ordered systems form so rapidly? Disk formation is a complex process. It requires the gas falling onto the galaxy to conserve its angular momentum and gradually settle into a thin, stable plane. Any major mergers with other galaxies should have shattered this fragile disk, turning it instead into an elliptical or irregular cloud of stars. The sheer number of disk galaxies in the early universe suggests that their evolution may not have been as turbulent and chaotic as we once believed. Perhaps they grew not through constant mergers, but through what's called cold accretion, a smooth, organized inflow of cold gas from the intergalactic medium along the filaments of the cosmic web. This scenario allows a galaxy to build up mass without destroying its delicate disk structure. Furthermore, Webb has detected the presence of a bar, an elongated structure of stars at the center, in some of these early disk galaxies. This feature was also considered a hallmark of a mature, highly evolved galaxy. Bar formation is tied to complex gravitational instabilities within the spinning disk, a process that was also thought to require billions of years to complete. Webb's discoveries force us to revise the timeline for galaxy evolution. It appears the universe was capable of creating complex and ordered structures far earlier than we ever imagined. While this doesn't necessarily break the Standard Cosmological Model as dramatically as the mass discrepancy does, it certainly adds crucial new detail to the picture. It suggests that the processes governing galaxy morphology may be faster and more efficient than our simulations have previously shown. Perhaps the role of smooth accretion was underestimated, while the role of violent mergers was overestimated. Studying these ancient, ordered galaxies will help us better understand how our own Milky Way acquired its beautiful spiral form, and why we live in a relatively calm and stable stellar metropolis. At the heart of every major galaxy, including our own, lurks a monster, a supermassive black hole. These objects can weigh millions, even billions, of times the mass of our Sun. Their very existence is a long-standing mystery in cosmology, one that the findings of the Webb telescope have only deepened. Where did these giants come from, and how did they get so big so fast? The standard theory suggested that supermassive black holes grew in tandem with their host galaxies. They started as stellar mass black holes, the remnants of the very first, most massive stars. These seeds gradually gained mass by swallowing gas and stars and merging with each other during galactic collisions. This is a logical process, but it's incredibly slow. To balloon to 1 billion solar masses, a black hole would need to feed at the maximum possible rate, known as the Eddington limit, for virtually the entire age of the universe. Yet Webb and other observatories are finding quasars, actively growing supermassive black holes, present just 7 or 800 million years after the Big Bang. Crucially, the mass of these black holes already reaches 1 billion suns. This creates the exact same puzzle we face with the galaxies, a severe time constraint. There simply hasn't been enough time to grow such immense giants from tiny stellar seeds. This observation has become a key argument supporting theories of more massive primordial seeds, for instance, the direct collapse of gigantic gas clouds into black holes already weighing 100,000 solar masses. If you start with a seed that large, ballooning up to 1 billion suns in only a few 100 million years becomes much more feasible. Webb is contributing directly to this debate by detecting signs of active black holes in the very earliest, including those previously thought impossible galaxies. The spectra from some of these galaxies show characteristic emission lines generated by gas swirling rapidly around a central black hole. This suggests that massive black holes weren't just present in the early universe, they were actively feeding and profoundly influencing their host galaxies. This raises the fundamental chicken and egg question: which came first? Did the galaxy form first and then nurture a black hole at its core, or did a massive black hole appear first and subsequently gather the necessary material to build a galaxy around itself? Webb's observations show that in some early galaxies, the black hole's mass is abnormally large relative to the mass of the galaxy itself. In the modern universe, there is a clear correlation. The more massive the galaxy, the more massive its central black hole. But in the early universe, this ratio appears to have been inverted. Black holes seem to have been able to grow faster than their host galaxies. This suggests that a top-down scenario, where massive black hole seeds play a crucial, initiating role in galaxy formation, might be closer to the truth. Unraveling the mystery of supermassive black hole origins is a core mission of modern astrophysics, and by allowing us to witness the very first stages of their growth, Webb offers us a unique opportunity to understand how these cosmic leviathans were born and how they shape the universe we observe today. Let's turn our attention to the earliest epoch of the universe, a period astronomers have dubbed the Cosmic Dawn. This era occurred after the Big Bang, following several 100 million years of the so-called Dark Ages, when the first stars and galaxies finally ignited across the cosmos. Their powerful ultraviolet radiation began ionizing the neutral hydrogen that pervaded all of space. This process, known as reionization, fundamentally transformed the universe, making it transparent from the opaque state it had been in. Understanding how and when reionization occurred is one of the primary scientific missions of the James Webb Space Telescope. Before Webb, we only had indirect evidence suggesting this process concluded roughly 1 billion years after the Big Bang. Crucially, we didn't know the identity of the main driver. Was the work done by countless small, faint galaxies, or was the heavy lifting handled by a few large, rare, and exceptionally bright ones? Webb's initial findings are dramatically revising this whole scenario. The detection of numerous unexpectedly bright and massive galaxies in those very early phases suggests they contributed far more to reionization than earlier models predicted. These galaxies were veritable photon factories. Their young, hot stellar populations pumped out enormous amounts of ultraviolet light. If large numbers of these galaxies existed, the reionization process could have started earlier and proceeded much faster than previous theoretical models had suggested. Webb allows us to study this process directly. By observing the spectra of incredibly distant quasars, astronomers can measure how their light is absorbed by intervening clouds of neutral hydrogen. Tracking how this absorption changes over distance, and thus over time, allows scientists to map how bubbles of ionized hydrogen grew and merged until they eventually permeated the entire cosmos. Webb's early data confirms that reionization was a complex and patchy process. Crucially, it appears to have concluded rather quickly, which strongly reinforces the argument that the primary sources of ionizing radiation were these larger, brighter galaxies. rather than a mere distribution of faint dwarfs. This finding, in turn, supports the idea that galaxy formation in the early universe was a much faster and more efficient process than we had previously modeled. Thus, the mystery of the cosmic dawn and the existence of these impossible early galaxies are intimately intertwined. If we can truly grasp how these primordial giants emerged, we will undoubtedly understand how they illuminated and transformed the entire cosmos. Investigating this era is akin to performing an archaeological dig on a cosmological scale. Webb allows us to peel back the veils of time, layer by layer, to witness how light was born from the primordial darkness and how the universe gradually evolved into the structure we see today. This provides fundamental knowledge about our own origins, as the atoms that compose our bodies were once forged within those very first stars and galaxies. Beyond just individual galaxies, the James Webb Space Telescope allows us to investigate much larger structures, galaxy clusters and protoclusters. These are the most massive gravitationally bound objects in the entire universe. In the modern universe, these clusters can contain thousands of galaxies, vast reservoirs of hot gas, and giant halos of dark matter. According to the Standard Hierarchical Model of structure formation, assembling these megastructures should take an incredibly long time, many billions of years. Finding a fully formed, mature cluster in the early universe, therefore, should be nearly impossible. However, Webb is designed to find their ancestors, the so-called protoclusters. These are regions in the early universe where the density of galaxies was significantly higher than average. While these galaxies haven't yet merged into a single colossal object, they are already gravitationally bound, destined to eventually form a massive cluster. Observations of these protoclusters give us a unique opportunity to witness the assembly of the universe's largest structures in cosmological real time. And in this area, Webb is also delivering surprises. It is finding these ultra-dense regions at astonishingly high redshifts, meaning they existed during extremely early epochs. This suggests that the earliest seeds for future galactic megacities were sown remarkably early. Furthermore, the galaxies within these protoclusters appear to evolve faster than their lonely counterparts in less dense regions. They collide and merge more frequently, exhibit more vigorous star formation, and their central black holes grow more rapidly. This phenomenon, known as environmental effects, demonstrates that a galaxy's ultimate fate is largely determined by its cosmic neighborhood. By observing protoclusters, Webb allows us to test the predictions of cosmological models on the grandest scales. The standard lambda CDM model makes fairly precise predictions about how many clusters of a certain mass should exist at different epochs. If Webb finds too many massive protoclusters forming too early, it would be another very serious challenge to the standard model. This would imply that gravitational collapse on large scales occurred faster than we currently understand. This could point to fundamental issues, either with our understanding of gravity itself or with the nature of dark matter and dark energy. Currently, data regarding protoclusters is still accumulating, and it's too early to draw definitive conclusions. However, this area of research is one of the most promising. By studying these cosmic construction zones, we can not only understand how galactic metropolises were assembled, but also test the most fundamental laws governing our universe. Every newly discovered protocluster is another piece in our gigantic puzzle, and Webb is allowing us to find these pieces during the earliest stages of the cosmic assembly. We've talked a lot about stars and galaxies, but they only make up a tiny fraction of the normal baryonic matter in the universe. The vast majority, about 80 to 90%, isn't inside galaxies, it's in the immense space between them. This diffuse environment is called the intergalactic medium, and it consists mostly of hydrogen and helium, organized into a colossal structure known as the cosmic web. This web is made up of dense threads or filaments which intersect at nodes. Galaxies form precisely within these nodes and along these filaments, fed by the gas flowing along these cosmic rivers. Studying the cosmic web is key to understanding how galaxies acquire the fuel necessary for their growth. For a long time, directly observing the cosmic web was nearly impossible because the gas is simply too diffuse and dim. We knew of its existence mainly through computer simulations and indirect evidence, specifically absorption lines in the spectra of distant quasars. As a quasar's light passes through a filament, the gas absorbs some of it, leaving a characteristic fingerprint in the spectrum. The James Webb Space Telescope, with its unprecedented sensitivity, is finally giving us the ability to see the web itself rather than just its shadow. Using specialized instruments like integral field spectrographs, Webb can map the faint hydrogen emission within the filaments that feed young galaxies. The first of these observations have already yielded stunning results. Scientists have been able to directly visualize cold gas flowing from the intergalactic medium along 3 distinct filaments, converging at a point where a cluster of young galaxies is forming. This provides direct visual confirmation of the cold accretion model we discussed previously. These observations show that galaxies are not isolated islands but active nodes within a giant cosmic ecosystem. Their growth and evolution are inextricably linked to this web. If we want to understand why some galaxies in the early universe grew so rapidly, we need to understand how this fuel delivery system operated. Perhaps in certain regions the cosmic web was much denser and fuller than the average. This could have provided the continuous abundant flow of gas necessary to form these seemingly impossible galaxies. Webb will be able to produce detailed maps of these structures surrounding numerous young galaxies. This will allow us to determine how typical filament feeding is, how the gas composition and temperature change as it approaches the galaxy, and critically, how this process influences star formation. Studying the cosmic web represents a new frontier in galaxy formation research. It's like we were studying cities without knowing anything about the roads, rivers, and trade routes that connect and sustain them. Webb is finally giving us a chance to see this hidden infrastructure of the universe and understand how it governs the life and death of galaxies. Let's refocus on exactly how scientists handle this data, giving us a clearer picture of just how complex and multi-layered the process of scientific discovery truly is. When Webb sends an image back to Earth, it's not a beautiful, finished photograph. Instead, it's a massive array of raw data, just numbers representing the brightness values of every pixel across multiple filters and spectral elements. The first stage is image processing. Specialized software pipelines work to strip away artifacts, noise from the detector, cosmic ray hits, and subtract the background sky glow. This is complex technical work demanding a deep understanding of the instruments themselves. Next comes the scientific analysis. Astronomers identify thousands of objects in the image. For each one, they meticulously measure the brightness across every available filter, a process known as photometry. This data is then used to construct the object's spectral energy distribution, or SED. The next crucial step is determining the redshift, which tells us the distance to the galaxy. There are 2 primary methods. The first, the photometric method, relies on finding a characteristic break in the galaxy's spectrum, typically caused by the absorption of light by neutral hydrogen. The specific filter where this break appears allows astronomers to estimate the redshift roughly. This method is fast, allowing them to process thousands of galaxies, but it's less precise and prone to occasional errors. The second method, spectroscopy, is far more reliable. The telescope splits the galaxy's light into a spectrum, a rainbow, and scientists search within it for familiar emission or absorption lines of chemical elements. The shift of these lines relative to their known laboratory positions directly and accurately reveals the redshift. Spectroscopic confirmation is universally considered the gold standard for determining cosmic distances. Many of the initial candidates for those impossible galaxies were first identified using the less precise photometric method. The main goal now is to obtain spectra for all of them to definitively confirm their nature and distance. This demands lengthy observation time, but it is absolutely necessary to ensure we are not chasing ghosts. Once the distance is confirmed, the most complicated phase begins, determining the galaxy's physical properties, its mass, age, and star formation rate. As we've discussed, this involves complex computer modeling, comparing theoretical spectra against the observed data. This step introduces a huge amount of uncertainty dependent on the choice of model, the initial mass function assumed, dust absorption laws, and other parameters. So, when the news reports an impossible galaxy discovery, it's crucial to understand that this is the result of a long, intricate chain of analysis, where every single step has its own set of assumptions and potential errors. The scientific community is currently working hard to verify and cross-check every stage. Different research groups are applying their own distinct methodologies to the same data to ensure the reliability of the findings. New observations are being scheduled specifically to reduce these uncertainties. This entire vetting process can take years. But this is exactly how science works, through doubt, rigorous testing, and continuous refinement. Webb's findings are not a final verdict, but the beginning of a thrilling investigation that may just lead us to new physics. One of the most powerful tools in Webb's arsenal is its ability to perform not just imaging, but also spectroscopy on hundreds of objects simultaneously. This is achieved using the NIR-SPEC instrument, which features a unique technology, the micro-shutter array. Imagine a postage stamp-sized chip composed of 250,000 tiny windows, each of which can be individually opened or closed. Before an observation begins, scientists capture an image of the target field. They then program the array to open only the windows positioned directly over the galaxies of interest. Light from these galaxies passes through the open shutters and onto the spectrograph, where it is dispersed into individual spectra. Light from everything else, the background sky and other objects, is blocked. This technology allows us to obtain high-quality spectra for well over 100 galaxies in a single observation, making it orders of magnitude more efficient than anything previously possible. So what exactly can a galaxy's spectrum tell us? Quite a lot. First, as previously mentioned, it provides a precise value for the galaxy's redshift. Second, by examining the shape and intensity of emission lines, such as hydrogen or oxygen, we can determine the galaxy's star formation rate, its chemical composition, or metallicity, and the density and temperature of its gas. The width of these lines also allows us to measure the internal motion of the gas, which in turn helps estimate the galaxy's total mass, including dark matter. Third, the continuous spectrum, or continuum, helps us determine the type and age of the stellar population. Young, hot stars emit more light in the blue end of the spectrum, while older, cooler stars dominate the red end. By comparing the observed continuum against stellar models, scientists can reconstruct the galaxy's star formation history. For these impossible galaxies, obtaining spectra is absolutely crucial. Spectroscopy allows researchers to distinguish, for example, between a truly massive galaxy with an ancient stellar population and a young, highly active galaxy undergoing a fierce burst of star formation that simply makes it appear anomalously bright. Furthermore, the spectrum can reveal the presence of an active galactic nucleus, or quasar, which can heavily skew mass estimates based purely on photometry. The first spectroscopic observations of the most intriguing candidates are already underway, and results are beginning to trickle in. In some cases, they confirm the extreme properties initially found through photometry. In others, it turns out the object is either at a different distance entirely, or its properties are not as anomalous as first thought. For instance, one of the earliest and most famous impossible galaxies discovered by Webb was later found, through spectroscopy, to be significantly less massive and younger than initially estimated. This underscores the vital importance of rigorous verification. But even if some candidates are ruled out, others remain whose anomalous properties are confirmed by spectroscopy, and every single confirmed object drives a nail into the coffin of older assumptions about galaxy formation. Webb's spectroscopy is, without a doubt, our most reliable tool for investigating this cosmic mystery. Let's imagine that future observations confirm our worst fears. The early universe truly holds a significant number of galaxies whose size and maturity simply don't align with the Standard Cosmological Model. What would this mean for science as a whole? It would mean what physicists call a crisis in cosmology. And actually, That's a fantastic thing. Crises in science are the engine of progress. They are the driving force behind paradigm shifts and the greatest discoveries. Let's look back at history. At the end of the 19th century, physics seemed almost complete. Newtonian mechanics and Maxwell's electrodynamics apparently described everything in existence. All that remained were two little clouds on the horizon, the problem of black-body radiation and the null result of the Michelson-Morley experiment. These little clouds ultimately sparked two revolutions, the creation of quantum mechanics and the theory of relativity, fundamentally altering our view of the world. We might be in a similar situation today. We have the incredibly successful Lambda CDM, Standard Cosmological Model, which beautifully describes a vast amount of observational data. But cracks are beginning to show. One of these cracks is the so-called Hubble tension, the discrepancy in the rate of the universe's expansion as measured by different methods. The other crack is precisely this problem of the impossible Webb galaxies. These issues could be those very clouds pointing toward the necessity of new physics. Perhaps we need to revise our understanding of the nature of dark matter. Maybe it's not just a single particle, but an entire dark sector with new particles and interactions. Maybe we need to modify Einstein's theory of gravity. Or perhaps we are on the verge of discovering completely new components of the universe that we never even suspected existed. Of course, it might turn out that the solution lies within the framework of existing physics. Perhaps we simply misunderstand certain astrophysical processes, such as the formation of the first stars. That would be a less revolutionary, but no less important outcome, one that would significantly deepen our knowledge. In any case, we are living in an incredibly exciting time. The James Webb Space Telescope isn't just an instrument for taking beautiful pictures. It is a machine designed to test our most fundamental theories about the cosmos. It confronts us with questions for which we currently have no answers. And the search for these answers will stimulate the development of theoretical physics and astronomy for decades to come. Perhaps in 10 or 20 years, our cosmology textbooks will begin with a chapter dedicated to Webb's discoveries, the discoveries that forced us to completely rethink our picture of the universe. And it is truly thrilling to be both witnesses and participants in this scientific revolution. While the primary focus remains on the earliest and most distant galaxies, the James Webb Space Telescope is a versatile instrument that contributes immensely to studying nearer, more modern galaxies as well. These observations are equally crucial because they allow us to see the end result of the processes that occurred in the early universe, giving us a deeper understanding of the entire evolutionary chain. Thanks to its infrared sensitivity, Webb can pierce through the dense clouds of dust that obscure the centers of many nearby galaxies, including our own Milky Way. This capability allows us to study the star formation processes happening there right now with unprecedented detail. We can resolve individual protostars and the planetary disks surrounding them, which helps us understand how our own solar system formed. Webb also facilitates detailed studies of the stellar populations within nearby galaxies. It can resolve individual stars even in galaxies located several megaparsecs away. This makes it possible to construct color magnitude diagrams for millions of stars and from those reconstruct the star formation history across different regions of a galaxy with incredible accuracy. We can determine when and where bursts of activity occurred within the galaxy and when it was resting. It's like reading the tree rings of a galaxy. Furthermore, Webb studies the dynamics of stars and gas in nearby galaxies. This allows for precise measurements of mass distribution, including that of invisible dark matter. By comparing detailed maps of dark matter distribution in modern galaxies with predictions from various theories, such as cold, warm, or self-interacting dark matter, we can place very tight constraints on its properties. This provides an independent way to test the very same theories we attempt to use when explaining the early galaxies. Observing nearby galaxies also helps us calibrate our methods. For instance, by thoroughly studying known star-forming regions, we can refine the models we later use to interpret data from distant objects. By understanding how the initial mass function or dust properties behave under different conditions in the local universe, we can make more informed assumptions about how they might have behaved in the past. Thus, Webb operates as a two-way time machine. It looks into the deep past to witness the beginning, while simultaneously studying the present in incredible detail to understand the final outcome. Only by combining these two approaches can we construct a complete and consistent picture of how our universe, and we ourselves, came into existence. Let's talk about the future. The James Webb Space Telescope is built to last for 10, perhaps even 20 years. Its mission has only just begun. What discoveries await us? First up, statistics. Right now, we're talking about a few dozen candidates for those anomalously massive early galaxies. Over the next few years, Webb will conduct even deeper and wider surveys of the sky, like the JWST project. This will increase our sample size of these objects by hundreds of times. We'll be able to determine just how common these galaxies really were, instead of seeing them as mere rare exceptions. Statistics is a powerful tool for testing cosmological models. Every model predicts a specific number of massive objects at a given redshift. By comparing these predictions to our observations, we can start ruling out some theories and narrow down the range of possible explanations. Secondly, detailed analysis. The most intriguing and confirmed targets will undergo extremely long and deep follow-up observations. Using ultra-high-resolution spectroscopy, Webb will be able to study the chemical composition of these galaxies with incredible precision. We might even be able to spot the chemical fingerprints of the very first population 3 stars, assuming they were present. We can measure their internal dynamics, whether they are rotating as neat disks or are the result of chaotic mergers. We'll also be able to map star formation within these galaxies to understand exactly where and how it is taking place. Thirdly, synergy with other observatories. Webb doesn't operate in a vacuum. Its discoveries will be supplemented and verified by other telescopes, both space-based and ground-based. For instance, X-ray observatories like Chandra can look for signs of active black holes in these galaxies. Radio telescopes, such as ALMA, can study the cold gas and dust, the fuel for star formation. And future giant ground-based telescopes, like the Extremely Large Telescope, ELT, or the 30-meter telescope, TMT, with their massive mirrors and adaptive optics, will be able to study these objects with even higher spatial resolution than Webb itself. Beyond these planned studies, we are also guaranteed completely unexpected discoveries. Every single time we have put a new, more powerful instrument towards studying the universe, we have found things we never anticipated. Hubble revealed the accelerated expansion of the universe and dark energy. Radio astronomy gave us pulsars and the cosmic microwave background radiation. What will Webb reveal? Perhaps we will find those elusive first stars. Perhaps we will find signs of life in exoplanet atmospheres. Or perhaps we will find something so bizarre that we currently don't even have the vocabulary to describe it. One thing is certain, the next decade will be a golden age for astronomy, and you and I are witnesses to the start of this new era of cosmic exploration. Let's return to our central theme, the lecture for sleep, and try to picture this impossible galaxy. Let's take a mental journey back 13.5 billion years into the past and billions of light years across space. We are in a young, turbulent universe. Space hasn't fully cooled yet. It is still permeated by the residual heat of the Big Bang. The darkness isn't absolute. It's faintly illuminated by the soft glow of the cosmic microwave background radiation. Galaxies, as we know them, barely exist yet. There are only small, loose clusters of the very first stars, dim pinpricks of light in the boundless gloom. And yet, amidst this primordial void, we see her. She is unlike her neighbors. She is colossal. She shines with a fierce, bluish-white light. This is the light of millions of young, giant stars, each one hundreds of times more massive and millions of times brighter than our own sun. They were born almost simultaneously in a truly grand burst of star formation that engulfed the entire galaxy. At her heart, a monster already lurks, a supermassive black hole ravenously devouring gas and causing the surrounding space to shine brighter than all the stars combined. Circling this blinding nucleus is a dense disk of gas and dust where, like precious gems, new star-forming regions are constantly igniting. This galaxy is a true metropolis in a world of small villages. It has already accumulated as much stellar mass as our own Milky Way gathered over billions of years. Where did she come from? How did she manage to grow so fast? Perhaps she was lucky enough to be born in a unique spot, a node in the cosmic web, where vast flowing rivers of primordial gas poured in from all directions. This continuous stream of fuel fed her insatiable hunger, allowing her to form stars at a ferocious rate. Or perhaps her story began even earlier. Maybe she didn't form just from gas, but from something far more exotic. Maybe her foundation was a giant halo of self-interacting dark matter, which collapsed much faster than ordinary matter. Or perhaps her seed was a directly collapsing black hole, 100,000 times the mass of the Sun, which then acted like a gravitational vacuum cleaner, sweeping up all the surrounding material. When we look at this galaxy, we see a challenge to our understanding, to our knowledge, and to our place in the universe. She tells us, "You thought you knew the rules of the game, think again." She compels us to be humble, to admit that our current theories are only the first, tentative steps toward understanding the infinitely complex and astonishing cosmos. This galaxy is more than just an object. It is a message from the deep past. A message that the universe is full of surprises and that the most important discoveries are still ahead of us. And as we reflect on this mystery, we can feel ourselves becoming part of something much grander, part of this great cosmic story that began billions of years ago with these impossible yet beautiful creations. When we look at the problem of these impossible early galaxies, it's crucial to understand that this issue doesn't exist in a vacuum. Over the past few years, cosmology has seen a build-up of other discrepancies and tensions that strongly suggest something is fundamentally wrong with the standard lambda CDM model. The most famous of these is the so-called Hubble tension. Essentially, there are two primary ways to measure the current expansion rate of the universe, known as the Hubble constant. The first is the local method. We measure distances to nearby galaxies using standard candles, like Cepheids and Type Ia supernovae, and calculate how quickly they are moving away from us. This technique gives us a value for the Hubble constant around 73 kilometers per second per megaparsec. The second is the cosmological method. We use data from the cosmic microwave background, the light left over from the Big Bang, and apply the Standard Cosmological Model to predict what the Hubble constant should be today. This method yields a value around 67 kilometers per second per megaparsec. The difference between these two values, 73 versus 67, is statistically extremely significant. This isn't just a measurement error, it represents a fundamental disagreement, suggesting either systematic errors in one of the techniques or that the model linking the early and late universe is fundamentally incomplete or incorrect. Interestingly, some of the theories proposed to solve the early massive galaxy problem might also help alleviate the Hubble tension. For example, models involving dynamic dark energy, which behaved differently in the past, could alter the expansion history of the universe in a way that reconciles these two disparate measurements. Another major discrepancy is the so-called S8 crisis. This parameter measures how clumpy or structured the universe is on large scales. Measurements of S8 based on the cosmic microwave background also disagree with measurements derived from observations of galaxy distribution in the more local universe. Again, this suggests that the growth of structures in the universe didn't proceed exactly as the standard model predicts. Perhaps structure formation happened faster in earlier epochs, which might explain those massive Webb galaxies, and then slowed down later. All of these problems, the Hubble tension, the S8 crisis, and the early massive galaxies, might simply be symptoms of the same deeper illness within the standard model. They suggest we are missing some fundamental piece of physics or a new cosmic ingredient. For instance, If dark matter could decay or interact with dark energy, this could influence all these observed quantities. Right now, we don't have a single unifying theory that elegantly solves all these issues simultaneously. But the very existence of these challenges makes modern cosmology an incredibly exciting field. We are standing on the brink of a potential paradigm shift, and the JWST data is playing a pivotal role. It adds another highly significant piece to the puzzle, one that might finally help us see the complete picture. Let's go back to the process of gas turning into stars, because this is truly the crux of the matter. The efficiency of this process is a key parameter that dictates how fast a galaxy can accumulate mass. In modern galaxies, this efficiency is surprisingly low. Only a tiny fraction, a few percent, of the gas within a galaxy actually converts into stars during a single pass through a spiral arm or other dense structure. The majority of the gas either remains in the interstellar medium or is violently expelled back into intergalactic space by supernova explosions. To explain the existence of these impossible galaxies within the framework of standard cosmology, we must assume that in the early universe this efficiency was orders of magnitude greater. Virtually all gas that entered a galaxy would have had to immediately and entirely convert into stars. Why might that have been the case? One leading hypothesis relates to the lack of metals, heavy elements. Paradoxically, their very absence may have promoted more effective star formation in those earliest stages. The key is that for a star to form, a gas cloud needs to collapse under its own gravity. This process is resisted by the gas's internal pressure. For the collapse to proceed, the cloud must efficiently shed heat. In other words, it must cool. In the primordial gas, composed solely of hydrogen and helium, the only effective cooling mechanism was the radiation of molecular hydrogen. This mechanism, however, only works within a specific range of temperatures and densities. This limitation meant that the gas couldn't fragment extensively. Rather than breaking up into many small knots that give birth to small stars, as we see today, the giant clouds collapsed almost whole, forming extremely massive stars. This scenario helps explain why the very first stars were likely stellar giants. Another idea involves the higher pressure and density of the intergalactic medium in the early universe. Young galaxies were literally squeezed from all sides, which could have accelerated the collapse of internal gas and triggered violent bursts of star formation, or starbursts. Furthermore, mechanisms that currently suppress star formation were either absent or significantly weaker in the early universe. Take, for instance, magnetic fields. In modern galaxies, magnetic fields play a crucial role in supporting gas clouds and resisting their gravitational collapse. In the very first galaxies, magnetic fields were likely far weaker, thus easing the path for star formation. However, all these beneficial factors had to contend with powerful feedback from those first stars themselves. As mentioned, their intense radiation and subsequent supernova explosions should have accelerated and heated the surrounding gas, potentially halting star formation entirely. It creates a kind of race. Can the galaxy turn its gas into stars faster than those very stars destroy the environment needed for new formation? Webb's observations suggest that the early galaxies were winning this race. This may indicate that the feedback mechanisms were not as effective as we previously assumed. Perhaps the gas in early galaxies was simply so dense that the radiation and explosions couldn't disperse it. Or maybe the energy from supernovae somehow escaped the galaxy through certain channels, bypassing the main gas reservoir. Understanding this delicate balance between fueling and feedback is the key to unraveling the mystery of rapid galactic growth. Now let's turn our attention to our own galaxy, the Milky Way, and view it through the lens of Webb's discoveries. Can the story of our home galaxy offer any clues about the processes at work in the early universe? The Milky Way is a large, fairly typical spiral galaxy today, but it didn't start out like this. It is the end product of a long and violent history of cosmic mergers and cannibalism. By studying the motion and chemical makeup of the stars within our galaxy, astronomers have learned to reconstruct its history, a method appropriately dubbed galactic archaeology. It turns out that our galactic halo, the sparse, spherical region enveloping the Milky Way's main disk is composed of countless stellar streams and star groups. Each of these streams is the surviving residue of a small dwarf galaxy, long ago devoured and ripped apart by the Milky Way's immense tidal forces. One of the most significant events of this kind occurred roughly 8 to 10 billion years ago, when the Milky Way violently merged with a sizable galaxy that astronomers nicknamed Gaia Enceladus, or more playfully, the Sausage. This cataclysmic impact profoundly shook our galaxy, and it is likely what led to the formation of its thick, stellar disk. But what came before? Galactic archaeology allows us to look even further back in time. By analyzing the oldest stars in our galaxy, the so-called population 2 stars, which are almost devoid of heavy elements, we can find traces of the very first building blocks that assembled the Milky Way. These stars are true, living fossils, essentially the same age as the universe itself. Recently, by analyzing data from the Gaia Space Telescope, researchers identified 2 groups of extremely ancient stars. These appear to be the remnants of 2 distinct proto-galaxies that merged at the very dawn of the Milky Way's history over 12 billion years ago. These foundational proto-galaxies were named Shakti and Shiva, representing some of the earliest cosmic bricks from which our galaxy began to build itself. This discovery confirms that the hierarchical assembly process, predicted by the Standard Cosmological Model, did indeed take place. Crucially, this doesn't contradict Webb's findings, rather it complements them perfectly. The Milky Way appears to be a case study of a normal galaxy, one that grew relatively slowly and followed the established evolutionary path. Conversely, Webb's impossible galaxies seem to have taken an accelerated alternative route to development. Perhaps they originated in extremely dense regions of the universe, or maybe they simply had the luck of beginning with more massive seeds. By studying normal galaxies like our own and comparing them to these extreme examples from the early universe, we can better gauge the full range of possible evolutionary paths and identify the key factors that determine the fate of any given galaxy. Perhaps our Milky Way is best described as a provincial galaxy, growing up in relative tranquility, while Webb's impossible galaxies were the early metropolitan megacities, thrown into the center of turbulent cosmic events right from the start. Whenever we discuss galaxy formation, we must confront a process that is both crucial and incredibly challenging to model: turbulence. The interstellar medium, or ISM, is far from being a calm, homogeneous gas. Instead, it's a turbulent, bubbling cauldron full of chaotic motions, vortices, and shock waves operating across all scales. This turbulence plays a dual role. On the one hand, it counteracts star formation by supporting gas clouds. It generates extra pressure that resists gravitational collapse. On the other hand, turbulence itself creates strong local compressions. In these pockets of high density, gravity finally takes hold, triggering the very conditions necessary for stars to form. Thus, turbulence simultaneously inhibits and facilitates the process of stellar birth. The sources of turbulence in young galaxies were numerous and complex. They include the accretion of gas from the intergalactic medium, which was often lumpy and non-uniform. There were also gravitational instabilities within the rotating galactic disk, and critically, there is stellar feedback, specifically supernova explosions, which inject vast amounts of energy into the ISM, generating powerful turbulent flows. Understanding how all these processes interacted under the conditions of the early universe is exceptionally challenging. Our current computer simulations cannot yet span the enormous range of scales involved, from the giant filaments of the cosmic web down to the tiny, dense protostellar cores. To bridge this gap, scientists rely on subgrid models, which describe small-scale physics using simplified phenomenological rules. The key to unlocking the mystery of the so-called impossible galaxies may in fact reside within these very subgrid models. Perhaps our current modeling misrepresents how turbulence affects star formation, especially given the low metal content and high gas densities prevalent in the early universe. For instance, if turbulence in primordial galaxies was more compressible, It would naturally lead to the formation of much denser structures and consequently far more efficient star formation. Alternatively, we might be underestimating how supernova energy interacts with a highly turbulent medium. It is possible that under specific conditions, instead of driving gas out, this energy compresses it, triggering entirely new waves of stellar birth. This area of research currently sits at the forefront of theoretical astrophysics. Scientists are hard at work developing new, more sophisticated hydrodynamic simulations designed to account for turbulence physics with much greater precision. Crucially, observations from the James Webb Space Telescope provide the critical data needed for these simulations. By studying the gas kinematics in distant galaxies, Webb can directly measure the characteristics of turbulence, allowing us to accurately calibrate our theoretical models. This is a perfect example of how observation and theory advance hand in hand. Webb presents theorists with complex new challenges, and the theorists, in turn, develop the sophisticated models required to better interpret Webb's groundbreaking data. It is through this vital dialogue that new scientific understanding is forged. We've used the word galaxy frequently in our discussion, but what exactly do we mean by that term when referring to the very first objects in the universe? In the modern universe, we have a clear classification system: spiral, elliptical, and irregular galaxies. However, these earliest objects might have been something else entirely. We might call them proto-galaxies or perhaps even galactic seeds. They likely lacked a well-defined structure. Instead, they were more like giant, chaotic star-forming complexes composed of numerous dense knots or clumps, each potentially the size of a small modern galaxy. Webb, with its exceptional resolution, allows us to begin probing the internal structure of these ancient objects. In some images, we see that they are far from smooth or uniform. They consist of several bright, compact nodes embedded within a more diffuse halo. This could be evidence that we are witnessing the process of hierarchical assembly in action. Perhaps these nodes are small galaxies currently in the process of merging to form one single, larger object. If this is the case, the system's total mass might not actually be anomalous. It simply means we are observing several objects clustered closely together, which we are currently mistaking for a single, gigantic galaxy. However, in other cases, these objects appear surprisingly compact and symmetrical, which argues against the merging scenario. They look more like a single, monolithic entity where star formation is occurring with incredible intensity. This brings us back to the concept of the so-called blue compact dwarfs, or P-galaxies, which are observed in the nearby universe. These are small but extremely active galaxies undergoing one massive burst of star formation. It is possible that the first impossible galaxies were exactly this: extreme, scaled-up versions of these P-galaxies. Understanding the true nature of these objects is crucial. If they are genuinely monolithic, rapidly formed systems, this poses a serious challenge to the Standard Model. Conversely, if they are groups of merging objects, it actually confirms the hierarchical scenario, though it pushes the timeline much earlier into the universe's history. To distinguish between these two scenarios, we once again need spectroscopy. By studying the spectra of different parts of these objects, we can determine whether they move as a single unit or whether they possess different velocities, which is characteristic of a merger. We can also compare their chemical compositions to understand if they formed simultaneously or separately. This work is just beginning, but it promises to illuminate the very first steps in galaxy assembly. Webb allows us to move beyond simply detecting these objects to performing a detailed anatomy of them, an immense leap forward in our understanding of the cosmic dawn. When discussing the distant cosmos, one question inevitably pops up: what role does dust play? Cosmic dust is made up of tiny solid particles, primarily carbon, and silicates. These form in the atmospheres of old, dying stars and are also blasted out during supernova explosions. In modern galaxies, dust is hugely important. It absorbs the light from young, hot stars, mostly in the ultraviolet and visible wavelengths, and then re-radiates that energy in the far infrared. This process is why many active galaxies in the present-day universe are almost invisible to optical telescopes, yet they shine brilliantly in infrared light. So, what about the early universe? Since the heavy elements that form dust were only just beginning to be produced by the first stars, the expectation was that those early galaxies would be essentially dust-free. They should have been incredibly transparent and bright in the ultraviolet. However, observations from the James Webb Space Telescope, JWST, and other instruments like ALMA are completely changing this picture. We've found that even the most distant galaxies, those seen within the universe's first billion years, already contain a substantial amount of dust. This poses a major new puzzle. Where did all this dust come from so quickly? Standard dust sources like evolved, low-mass stars simply wouldn't have had enough time to form and produce the required amount of dust. This strongly suggests that the primary source of dust in the early cosmos was likely the rapid explosion of supernovae left behind by the very first, most massive stars. But even when factoring this in, current models still predict a much smaller dust abundance than what we are actually observing. The presence of large amounts of dust in these early galaxies has several profound implications. First, it tells us that the production of heavy elements and dust was far quicker and more efficient than previously assumed. This, in turn, might be linked to the concept of a modified initial mass function. If the early universe produced many more massive stars, they would have rapidly enriched their environment with these elements and dust. Second, dust significantly complicates the interpretation of our observations. As noted, dust makes a galaxy appear redder, a phenomenon that could be mistakenly interpreted as an indicator of an older stellar population or even greater distance. Misjudging the dust content can lead to significant errors when determining a galaxy's true mass and age. Webb is perfectly suited for studying this dusty, early universe. By operating in the infrared range, it can capture both the starlight that manages to penetrate the dust and the thermal emission radiated by the dust itself. This provides astronomers with a complete picture of the galaxy's energy budget, allowing them to accurately determine exactly how much light was absorbed and re-emitted. Studying the universe's first dust is key to understanding the initial chemical enrichment of the cosmos. It tells the story of how the very first solid particles emerged from a soup of pure hydrogen and helium, particles that would eventually become the fundamental building blocks for future planets, and perhaps for life itself. Let's broaden our perspective and consider the profound philosophical implications of these discoveries. Astronomy is the one science that has consistently forced humanity to redefine its place in the cosmos. Copernicus's discovery that Earth is not the center of the universe was more than just a scientific finding, it was a fundamental shift in our entire worldview. Similarly, the Hubble Space Telescope, by showing us billions of other galaxies, forced us to confront the sheer insignificance of our own place in the cosmic expanse. So what do the Webb discoveries tell us? They suggest that the universe is far more rapid and efficient than we ever imagined. It didn't spend billions of years undergoing slow, gradual evolution. Instead, it seems capable of forging complex, massive structures almost immediately after its inception. This radically changes our perception of time and complexity. We are accustomed to thinking of complexity as the byproduct of long, arduous evolution. But perhaps the cosmos possesses mechanisms for rapid, almost explosive growth in complexity. This has profound implications not just for astrophysics, but also for fields like biology or systems theory. Furthermore, these findings underscore the sheer power of the scientific method itself. We developed a beautiful, elegant theory, the Standard Cosmological Model. It served us well for decades, but the moment we deployed an instrument capable of testing it under new, extreme conditions, we found discrepancies. Science doesn't try to hide or ignore these contradictions. On the contrary, it focuses intently on them, because it is in these very anomalies that new knowledge lies hidden. This is a crucial lesson in intellectual honesty and openness to the new. It is also a humbling reminder of how little we truly know. We have explored only a minuscule fraction of the universe across a fleeting instant of its existence. To assume that we have already grasped all the fundamental laws is the height of intellectual arrogance. The universe constantly delivers surprises, and every new surprise is a gift, an opportunity to discover something new and astonishing. Finally, contemplating these ancient, seemingly impossible worlds inspires a profound sense of awe and wonder. To imagine these colossal stellar islands born at the very dawn of time, whose light has traveled further than the entire age of the Earth, is an exercise in imagination that pulls us far beyond our daily concerns. It allows us to touch something eternal and truly magnificent, and this perhaps is one of astronomy's greatest values. It expands not just our knowledge, but the capacity of our souls. It teaches us to look up, to ask the biggest questions, and never to cease marveling at the beauty and complexity of the world we are so lucky to inhabit. Let's circle back to one of the most intriguing alternative scenarios, the pivotal role of supermassive black holes acting as galaxy seeds. This concept, often called the top-down model, completely flips traditional cosmology on its head. Instead of a galaxy slowly nurturing a black hole at its core, this time the black hole serves as the catalyst, actively building the galaxy around itself. So, how might this process actually unfold? Imagine the early universe, where some exotic mechanism, say the direct collapse of massive gas clouds or supermassive stars, gives rise to a black hole weighing perhaps 100,000 solar masses. An object that massive instantly creates an immense gravitational potential well. It begins pulling in surrounding gas far more efficiently than a dark matter halo ever could. As this gas spirals inward, it forms a dense accretion disk around the black hole. Within this disk, conditions become perfect for explosive star formation. The gas density is extremely high, and the fierce radiation streaming off the accretion disk compresses nearby material, triggering new waves of stellar creation. Essentially, the galaxy doesn't grow from the inside out. It accretes, or grows onto, an already established black hole. This scenario boasts several appealing features. First, it elegantly resolves the timeline problem for both galaxies and supermassive black holes. We get two objects, a massive black hole and an actively forming galaxy, emerging simultaneously in the very early cosmos. Second, it helps explain observations we've already discussed. In some young galaxies, the black hole mass appears anomalously large relative to the mass of the host galaxy itself. In the top-down model, this ratio is perfectly natural, since the black hole was the initial structure. However, this model isn't without its challenges. The primary hurdle is figuring out where these massive seeds actually came from. The conditions required for direct gas collapse are extremely specific. You need vast amounts of gas that hasn't yet formed stars and remains pristine, free of heavy elements. It's still unclear how frequently these ideal conditions could have been met in the early universe. If this seeding mechanism was rare, it might explain a handful of extreme objects, but not the widespread emergence of early galactic giants. This is where the James Webb Space Telescope, or Webb, steps in to test the hypothesis. If the top-down model holds true, we should observe very bright, quasar-like cores within the earliest galaxies. We should also see specific correlations between the black hole's properties and its host galaxy's characteristics. For instance, the rate of star formation in the galaxy should be tightly coupled to the rate of accretion onto the black hole itself. Hunting for these black hole-born galaxies is one of Webb's most exciting tasks. If their existence is confirmed, it would redefine black holes not just as the end product of stellar and galactic evolution, but as active cosmic architects that shaped the universe from its very beginning. Let's turn our attention back to the properties of dark matter as they fundamentally underpin the entire structure of the universe. The standard cold, dark matter, or CDM model, has been incredibly successful in explaining the large-scale structure of the cosmos, the sprawling distribution of galaxies within the cosmic web. However, when we look at the scales of individual galaxies, the model has long faced persistent hurdles known as the small-scale problems. One of these is the missing satellites problem. CDM simulations predict that massive galaxies like the Milky Way should be surrounded by a huge number of small dark matter halos and consequently dwarf satellite galaxies. Yet observations reveal far fewer satellites than the theory predicts. Another issue is the too dense centers problem. Simulations forecast that dark matter density should dramatically increase at the very heart of a halo, forming a structure known as a cusp. Observations based on the rotation of gas and stars in real galaxies, however, often show a much shallower density profile referred to as a core. Various astrophysical mechanisms have been proposed to resolve these long-standing discrepancies. For instance, feedback from supernovae might blow out gas from small halos, preventing them from forming stars, thus solving the satellite problem. Or it could heat and puff up the central regions of the halos, thereby addressing the cusp problem. However, these explanations often felt somewhat forced and required significant fine-tuning of parameters. Now the findings from the Webb telescope add a new layer to these small-scale issues, the large-scale problem at early times. But this is forcing scientists to re-examine alternative dark matter models that might resolve all these issues simultaneously. For example, the self-interacting dark matter, or SIDM, model offers a promising path. If dark matter particles can collide and exchange energy, this naturally leads to the formation of cores in the halo centers, solving the cusp problem. It can also alter the formation process of the smallest halos, potentially resolving the satellite issue. Moreover, in the early universe, such interactions could accelerate the collapse of central halo regions, helping to explain the rapid growth of early galaxies, as we have already discussed. The fuzzy dark matter model, where particles behave more like waves than traditional particles, also predicts the formation of cores in galaxy centers and the suppression of the formation of the very smallest structures. Thus, it may turn out that Webb's impossible galaxies are not an isolated puzzle, but the crucial key to solving a whole complex of cosmological problems that have plagued scientists for decades. They could be the missing link that finally points us toward the true nature of dark matter. Webb, along with other telescopes, by meticulously mapping the dark matter distribution in various types of galaxies across different cosmic epochs, may soon provide the definitive answer to this fundamental question. Unlocking the nature of dark matter will undoubtedly be one of the greatest scientific achievements of the 21st century. As we explore various theoretical explanations, we must not lose sight of the possibility that what we are seeing is not the result of one novel process, but a potent combination of several factors. The universe seldom operates simply. Reality is more likely an intricate tapestry woven from diverse effects. Perhaps these impossible galaxies are the product of a perfect storm, a rare confluence where several favorable conditions aligned simultaneously. Let's explore this scenario. First, such a galaxy would have been born within an extremely dense node of the cosmic web, ensuring an abundant and continuous inflow of cold gas. This was a necessary, though not sufficient, condition. Second, the initial mass function within this galaxy was heavily skewed toward very massive stars. This accelerated chemical enrichment, potentially leading to more efficient gas cooling, and also facilitated the formation of massive seed black holes from the stellar remnants. Third, the feedback from these massive stars was, for some reason, less effective than usual. Perhaps due to the extremely high gas density or a specific geometry of its distribution, the energy released by supernovae dissipated without destroying the gas disk. It might have even compressed the disk, thereby stimulating further star formation. Fourth, the core of this galaxy might have housed a concentration of self-interacting dark matter, which collapsed faster than a typical dark matter halo, creating an additional center of gravity. If we aggregate all these factors, we might be able to explain the appearance of this galactic monster without resorting to truly radical new physics, such as modifying the laws of gravity. Individually, each factor might not yield the necessary result, but their synergy could lead to a qualitatively new outcome. The main challenge with this multi-factor approach is that it becomes incredibly difficult to test empirically. We need to determine the probability of such a combination of events occurring. If it is extremely rare, it might explain the existence of one or two black swans. However, this theory fails if the James Webb Space Telescope finds that such galaxies were actually commonplace in the early universe. Consequently, scientists are currently working along two main tracks. On one hand, they are searching for a single, simple, and elegant idea, a new particle or a new law that would explain everything. On the other hand, they are building increasingly complex and realistic computer simulations that incorporate as many known physical processes as possible, attempting to see if their combination can successfully reproduce the observed phenomena. Only time will tell which path leads to success, but the search itself, where bold theoretical hypotheses intertwine with meticulous modeling, is a beautiful demonstration of how modern science truly operates. The chemical evolution of the universe is another crucial area Webb is allowing us to study with unprecedented precision. All elements heavier than hydrogen and helium, what astronomers collectively refer to as metals, were forged inside stars. By tracking how the abundance of these elements changes over time and across different types of galaxies, we can reconstruct the star formation history of the cosmos. Before Webb, data on the chemical composition of galaxies during the first billion years was extremely sparse. Scientists expected these early galaxies to be incredibly pristine, containing metal abundances hundreds of times lower than our Sun. However, Webb's initial spectroscopic observations reveal that some of these early galaxies had already undergone rapid metal enrichment, reaching levels comparable to the Small Magellanic Cloud, the Milky Way's dwarf satellite galaxy. This strongly suggests that star formation within them was exceptionally intense and began remarkably early in cosmic history. They had sufficient time for multiple generations of massive stars to be born, run through their life cycles, and explode, effectively seeding the interstellar medium with the heavy elements they synthesized. Analyzing specific elemental ratios can offer deeper insights. For instance, the ratio of oxygen to iron is an excellent indicator of the timescales involved in star formation. Oxygen is primarily produced by massive stars that rapidly detonate as Type II supernovae, often just a few million years after they form. Iron, conversely, mainly comes from Type Ia supernovae, the spectacular explosions of white dwarfs, which happen much later, involving a time delay of hundreds of millions or even billions of years. If an ancient galaxy shows high oxygen content but low iron, it signifies that we are witnessing the immediate aftermath of a violent and recent starburst episode. Webb can measure the abundance of these different elements in distant galaxies using their distinct spectral emission lines. This capability allows us to perform chemical archaeology on the early universe. By studying the unique chemical signatures the first stars left behind, we can determine the initial mass function of those earliest stellar populations. Theory, for example, predicts that the supernovae remnants of population 3 stars would have produced a highly specific set of elements. Identifying galaxies with this anomalous chemical makeup is a key objective for Webb. This rapid chemical enrichment is also critical for understanding planet formation. Heavy elements are essential building blocks for planets, particularly rocky worlds like Earth. If the universe became enriched with metals and dust so early, it means the very first planets could theoretically have formed within the first billion years of cosmic history. This significantly expands the timescale available for life to have potentially emerged throughout the cosmos. While Webb cannot directly detect these early exoplanets by examining the chemical makeup of their host galaxies, it can tell us whether the necessary foundational conditions for their existence were present. Let's indulge in a little scientific speculation. What if the Milky Way had developed into one of those impossible galaxies? Imagine that our galaxy was born in one of the extremely dense regions of the early universe. Its history would likely have been entirely different. Instead of the slow, gradual assembly from dozens of small fragments over billions of years, it would have experienced one or more cataclysmic, all-consuming star formation bursts right at the start of its life. Virtually all of its gas would have been consumed in the first few 100 million years. As a result, the Milky Way we see today would be unrecognizable. It would likely be a giant elliptical galaxy, not a spiral. It wouldn't have beautiful spiral arms because there would be nothing left to form them. All the cold gas would have been depleted eons ago. The galaxy would primarily consist of old, red stars, slowly fading away. Astronomers have a term for this. It would be a red and dead galaxy. Life, if it could have arisen there at all, would face an entirely different reality. The night sky would be much dimmer and more uniform, lacking the brilliant sweeping band of the Milky Way, which is the light of young stars in our galaxy's disk. Moreover, the galaxy's early history would have been incredibly violent. Intense star formation would have meant a constant barrage of supernova explosions, powerful radiation from millions of hot stars, and the active galactic nucleus would ionize all the gas, and cosmic rays would saturate the entire volume. This would be an extremely hostile environment for the emergence and development of planetary life. Perhaps we are simply lucky that our Milky Way turned out to be a quiet achiever and a galactic provincial. Its slow, deliberate evolution allowed it to conserve its gas supply right up to the present day, enabling calm, continuous star formation. This created the stable conditions lasting billions of years that were likely necessary for complex life to germinate and thrive on one of its planets, Earth. This thought experiment demonstrates that we are not just a product of planetary evolution, but a direct consequence of our galaxy's entire history. Our existence is inextricably linked to the specific developmental path the Milky Way took. By studying other galaxies, especially those extreme early universe examples, we gain crucial insight into how unique or how typical our home truly is. This helps us address one of the deepest questions: are we alone in the universe? Understanding which types of galaxies are capable of supporting life and which are not is the essential first step toward finding that answer. As we gaze upon the breathtaking images captured by the James Webb Space Telescope, we must remember they represent more than just cutting-edge technology. They are the culmination of decades of human perseverance, collaboration, and sheer hard work. The concept for a large orbiting infrared telescope first emerged back in the 1980s, long before the launch of the Hubble. For nearly 40 years, thousands of scientists, engineers, programmers, and project managers from the United States, Europe, and Canada dedicated their expertise to this monumental endeavor. This project faced immense challenges. There were technical hurdles that seemed truly insurmountable. Repeated delays and massive budget overruns pushed the telescope to the brink of cancellation multiple times. Yet time and again, people who believed fiercely in its scientific merit fought to keep the project alive. The very necessity of developing new technologies for Webb led to countless innovations that found applications right here on Earth, for example, in medical fields like ophthalmic diagnostics. The Christmas Day launch in 2021 was merely the start of the mission's most critical and nerve-wracking phase. Over the subsequent month, the telescope had to execute hundreds of highly complex deployment operations in deep space. This involved deploying the sun shield, where all 5 layers had to be tensioned with perfect micron-level accuracy. It required extending the secondary mirror on its long boom arm and unfolding the wings of the primary mirror. Every single step was a one-shot operation with zero margin for error. A single malfunction could have resulted in the total loss of the $10 billion mission. The entire world watched this incredibly intricate cosmic ballet with bated breath, and flawlessly it worked. It was a true triumph of human ingenuity and our capacity for complex, coordinated effort. Deployment was followed by several months of painstaking alignment and calibration. The 18 segments of the primary mirror had to be phased together into a single surface with nanometer precision, a feat achieved through thousands of microscopic adjustments to each segment. Finally, in the summer of 2022, the world saw Webb's first scientific images. They surpassed even our wildest expectations. This entire story serves as a potent reminder that great scientific breakthroughs do not happen in isolation. Behind every discovery lies immense human labor. And when we look at an impossible galaxy, we shouldn't just see a challenge to scientific theories. We must recognize the profound capability of humankind when we unite our efforts toward a single, magnificent goal: the exploration of the universe. Let's circle back to the fundamental constants. The Standard Cosmological Model rests on a core assumption that the laws of physics and constants like the speed of light, the gravitational constant, and the fine structure constant are truly invariant across time and space. But what if that assumption is wrong? The notion that these constants might vary isn't new at all. Theoretical physicists have debated it for ages, particularly within theories aiming to unify gravity and quantum mechanics like string theory. Some of these models predict that the values we measure today might just be frozen relics of a dynamic field, a field that could have behaved very differently in the early universe. Could variations in fundamental constants, especially in the early universe, be the key to explaining the emergence of those impossible early galaxies? Let's hypothesize that the gravitational constant, g, was slightly larger in the past than it is now. This would obviously accelerate the gravitational collapse of matter. Dark matter halos would grow faster, gas would fall into them more actively, and galaxies would have formed much, much earlier. It offers a very simple and elegant solution to the problem. However, this hypothesis carries massive implications. Changing the gravitational constant wouldn't just affect galaxy formation, it would impact every other cosmic process. It would alter the expansion rate of the universe. It would change the timeline of Big Bang nucleosynthesis, the process that created the light elements in the first minutes after the Big Bang. It would even change how stars evolve and function. We have extremely precise measurements, for instance, the ratios of light elements in the universe, and data from the cosmic microwave background radiation, which place incredibly stringent constraints on any possible variations of g. These constraints tell us that if g has changed at all, the change must have been infinitesimally small. The same challenge applies to other constants. For example, altering the fine structure constant, which dictates the strength of the electromagnetic force, would change how atoms emit and absorb light. We could detect such changes by looking at the spectra of distant quasars. While some studies have claimed to find evidence of such variations, those results remain highly controversial. In summary, while the idea of varying constants is intellectually seductive, it currently lacks compelling evidence and arguably raises more problems than it solves. Most scientists believe the solution to the Webb mystery should be found within the framework of standard physics, perhaps by adjusting the components of the universe like dark matter and dark energy, rather than rewriting its fundamental laws. But who knows, perhaps the James Webb Space Telescope or future experiments will finally uncover irrefutable proof that the laws of nature aren't quite so constant after all. That would represent the most profound revolution in our understanding of the cosmos since Einstein. As we conclude our lecture, let's address a question that often comes up in popular science discussions. Can the Webb telescope actually see the Big Bang itself? The answer is no, and there is a fundamental reason why. For the first 380,000 years after the Big Bang, the universe was incredibly hot and dense. It existed as an opaque plasma of protons, electrons, and photons. In this state, the universe was completely opaque to light. Photons couldn't travel freely. They were constantly scattered by free electrons. Think of it like trying to see through extremely dense fog or a cloud. This opaque epoch ended when the universe finally cooled enough for protons and electrons to combine into neutral hydrogen atoms, a process we call recombination. Once this happened, photons were finally free to stream through space. The light emitted at that exact moment is what we observe today as the cosmic microwave background, or CMB. This is the oldest photograph of the universe we can ever get using electromagnetic radiation. It shows us exactly what the universe looked like when it was 380,000 years old. It is fundamentally impossible to see any further back than that using light-based telescopes, whether they operate in the visible, infrared, or radio spectrum. It's similar to looking at the surface of the sun. We cannot see what happens inside because the interior is opaque. Therefore, Webb, being an infrared telescope, is bound by this exact same fundamental limit. However, Webb can get incredibly close to that epoch. It was designed to see the very first stars and galaxies, which are thought to have formed just 100 to 200 million years after the Big Bang, during the era we call the cosmic dawn. Observing these first structures is one of its primary missions. Are there other ways to peer past the wall of the CMB? Theoretically, yes. The universe was transparent to other types of particles, specifically neutrinos and gravitational waves. If we could build detectors sophisticated enough to capture the background neutrinos or the gravitational waves from the Big Bang itself, we would be able to see what happened during the very first seconds of the universe's life. This remains one of the most ambitious goals in future physics, but for now, Webb and its ability to capture those first galaxies represent our most powerful tool for studying how the universe emerged from its infancy and began to form the structures we see today. It cannot see the explosion itself, but it sees its immediate aftermath, the first sparks in the cooling darkness. Moving on in our discussion, let's also touch upon the so-called anthropic principle. This is a philosophical concept positing that we, as observers, exist in a universe with specific properties precisely because if it were any different, we simply wouldn't be here to observe it. For instance, had the fundamental constants been even slightly different, stars couldn't form, heavy elements like carbon couldn't be synthesized, and complex life would be impossible. The anthropic principle is often criticized not for being a scientific prediction, but rather for being a mere tautology. However, it becomes useful in the context of theories that hypothesize the existence of the multiverse, a hypothetical ensemble of many universes, each potentially featuring different physical laws and constant values. In this scenario, we simply reside in one of those rare universes where the conditions happen to be just right for our emergence. How does this connect to Webb's discoveries? If it turns out that the Standard Model is indeed wrong, and explaining the rapid formation of galaxies requires very specific and finely tuned initial conditions or laws that could strengthen the case for the anthropic principle, perhaps we live in a universe that isn't just habitable, but one that is also optimized for the speedy formation of galaxies, which are, in turn, necessary for creating stars and planets. For instance, if observations mandate self-interacting dark matter with a very specific interaction strength, we must ask, why did nature select this precise value? The anthropic principle might offer an explanation, because any other value would result in galaxies forming either too slowly or too quickly, preventing the emergence of observers. Naturally, this is a highly speculative line of reasoning. Most physicists prefer seeking explanations without resorting to the anthropic principle, instead striving for a fundamental theory that unequivocally predicts the observed parameters. Nevertheless, as we uncover more examples of fine-tuning in our universe, from the mass of the Higgs boson to the density of dark energy, the anthropic principle remains in the background as a possible, if controversial, explanation. Webb's findings, by adding another potential fine-tuning parameter, the universe's ability for ultra-fast structure formation, could make this debate even more relevant. They force us to consider not just how our universe is structured, but why it is structured this way and no other. Another crucial research area for Webb involves studying the so-called dark galaxies. These are hypothetical objects predicted by theory to exist, but which we have yet to reliably detect. What exactly are they? Within the Standard Cosmological Model, the first structures to form are halos made of dark matter. Gas should then fall into these halos and begin forming stars. However, the theory also predicts the existence of a huge population of small dark matter halos that, for various reasons, never accumulated gas, or perhaps they did, but the gas failed to form stars. For example, the gas might have been blown out too early by the intense radiation from neighboring, brighter galaxies. These objects should essentially be clumps of dark matter containing minimal amounts of gas, but almost entirely lacking stars. They are expected to be nearly invisible, hence the name dark galaxies. Finding them would provide crucial validation for the Standard Model on small scales and help solve the long-standing missing satellite problem. So, how do we find something that doesn't shine? There are a few methods. One involves searching for absorption lines in the spectra of distant quasars. If a dark galaxy lies along the line of sight between us and the quasar, its gas will leave a distinct fingerprint in the light spectrum. Another, more direct method is detecting the faint emission from the gas itself. This is where Webb, with its incredible sensitivity, could deliver a breakthrough. It might be able to pick up the extremely weak hydrogen emission from these dark objects, especially if they are located near a bright quasar that illuminates them, causing them to fluoresce. Recent results published by astronomers using the VLT telescope in Chile suggest they may have found several candidates for such dark galaxies. Webb will be able to conduct far more sensitive follow-up observations, either confirming or refuting those findings. Discovering a population of dark galaxies would be a triumph for the cold dark matter model. Conversely, their absence would constitute another serious argument against it. This would imply that dark matter cannot form such small halos, pointing instead toward models of warm or fuzzy dark matter. Thus, even the search for what is missing, or nearly invisible, can teach us profound lessons about the fundamental structure of the universe. And Webb remains our most powerful tool in these dark explorations. Let's return to one of the most astonishing aspects of the Webb telescope, its location at the L2 Lagrange point. Why was this distant, hard-to-reach spot chosen? In any system of two massive bodies, like the Sun and the Earth, there are 5 Lagrange points. These are specific positions where the gravitational pull of the two bodies and the centrifugal force perfectly balance out. An object placed there can remain stable, requiring only minimal fuel expenditure for orbital correction. The L2 point is located 1.5 million kilometers, about 1 million miles from Earth, directly along the line connecting the Sun and Earth, but situated behind Earth. This location offers several unique advantages crucial for an infrared telescope. Firstly, at L2, the telescope can constantly keep its back, its massive sun shield, facing the Sun, the Earth, and the Moon simultaneously. These three are the main sources of heat and light in the solar system. This arrangement allows the sensitive optics and instruments to be extremely well protected from external heat. If Webb were in low Earth orbit, like Hubble, it would constantly enter and exit the Earth's shadow. This would cause wild and rapid temperature swings, severely disrupting observations. Secondly, being so far from Earth means the telescope is entirely shielded from our planet's own thermal radiation and the interference caused by the Earth's atmosphere. Thirdly, the orbit around the L2 point is inherently stable. As mentioned, this minimizes fuel consumption needed to maintain its precise position. However, this location comes with one critical drawback. It is utterly inaccessible for repair. Hubble, in its low Earth orbit, was visited several times by astronauts on the space shuttle. They repaired it and installed new, more advanced instruments. This significantly extended Hubble's lifespan and expanded its scientific capabilities. With Webb, that option simply does not exist. Flying a crewed mission to L2 is a far more complex undertaking than going to the Moon. Consequently, the telescope was designed and built with the highest possible degree of reliability. All its systems are heavily redundant, but if something major fails, repair is impossible. This element makes the Webb mission even more dramatic. We truly have only one shot. This unique instrument, the result of decades of work, must successfully operate for its planned duration without failure. So far, it has handled this challenge brilliantly. Its location in the cold, stable environment of the L2 point is a key factor in its success, allowing it to achieve unprecedented sensitivity and peer into the most hidden corners of the universe. When astronomers search for the very first stars, they are looking for what are known as population 3 or POP3 stars. This hypothetical first generation formed exclusively from the primordial material remaining after the Big Bang. In other words, just hydrogen and helium. All other stars we observe today, including our Sun, population 1, and the older stars in the galactic halo, population 2, contain heavier elements, those forged by earlier generations of stars. POP3 stars would have possessed unique properties. The absence of metals, elements heavier than helium, which are crucial for cooling gas efficiently, meant that the protostellar clouds couldn't fragment extensively. Consequently, scientists believe these stars were overwhelmingly massive, ranging from tens to perhaps thousands of times the mass of the Sun. They would have been incredibly hot, boasting surface temperatures up to 100,000 degrees and shining millions of times brighter than the Sun, predominantly in the ultraviolet spectrum. Their lives would have been fleeting, lasting only a few million years. When they died, they would either detonate as a special kind of explosion called a pair instability supernova, or they would collapse directly into black holes. Crucially, these stars initiated the chemical enrichment of the universe and may have provided the first seeds necessary for the formation of supermassive black holes. Directly observing a single POP3 star is nearly impossible, even for the James Webb Space Telescope, or Webb. They are simply too faint due to the immense cosmic distances. However, there are several indirect detection methods. One involves searching for their distinct chemical signature within the spectra of very old stars in our own galaxy. If we find a star whose elemental composition is unique and aligns with the predicted fallout from a POP3 explosion, it would provide compelling proof of their existence. Another approach is to look for entire galaxies composed predominantly of POP3 stars. Such a galaxy should exhibit a very specific spectral profile, marked by strong ionized helium emission lines and extremely weak metal lines. Hunting for these objects remains a critical mission for Webb. There is a third, more exotic route: gravitational lensing. If a massive galaxy cluster happens to align perfectly between us and a distant POP3 star, its gravity can serve as a giant lens, magnifying the star's light enough for Webb to detect it. While this is an incredibly rare event, given the sheer number of targets Webb observes, it remains a distinct possibility. Detecting these first stars would undoubtedly stand as one of the greatest discoveries in astronomical history. It would be akin to finding the very first spark that ignited the enormous cosmic bonfire of our universe. And the James Webb Space Telescope offers us the best opportunity yet to witness that moment. Let's revisit the Standard Cosmological Model and its components, lambda CDM. Lambda stands for the cosmological constant, which represents dark energy. CDM stands for cold, dark matter. This model rests upon just 6 parameters which have been precisely determined through observations of the cosmic microwave background by the Planck satellite. These 6 numbers allow us to describe almost all the large-scale properties of our universe. This is an extraordinary intellectual achievement. However, the success of the model shouldn't obscure the fact that we have no idea what the nature of its 2 main components actually is. Dark matter and dark energy together account for 95% of the total mass energy of the universe, and we still don't know what they are. This can arguably be called the greatest failure of modern fundamental physics. We've essentially built a house without knowing what its walls or foundation are made of. Regarding dark matter, decades of searching for hypothetical particles, such as WIMPs or axions, in underground detectors and colliders have yet to yield any results. This leads many physicists to question the validity of this approach and look for alternatives, such as modifying gravity. The situation with dark energy is even more problematic. Theoretical calculations for the density of vacuum energy, which could play the role of dark energy, give a value that is off by 120 orders of magnitude, that's a 1 followed by 120 zeros, compared to the observed value. This is the largest discrepancy between theory and experiment in the history of science. It is famously known as the cosmological constant problem. In this context, Webb's findings take on special significance. They may be the first observational evidence that this strange, dark sector of the universe is far more complex than we previously imagined. Perhaps dark matter is not so simple and cold. Perhaps dark energy is not constant. If Webb and other future experiments confirm that we need new physics within the dark sector to explain the observations, it will open up a completely new direction for research. It could give theorists long-awaited clues about which direction to pursue in order to unravel these greatest mysteries of nature. So when we talk about an impossible galaxy, we are actually discussing something much bigger. We are talking about the possible beginning of the end of our ignorance regarding 95% of the universe. This is an incredibly exciting time where astronomical observations are moving to the forefront of fundamental physics and could lead to a revolution in our understanding of reality. To wrap up our lecture, let's take a moment to summarize and cast our eyes once more over the grand picture being painted by the James Webb Space Telescope. We started with what seemed at first glance like a simple observation, the detection of galaxies in the early universe that appeared far too massive for their age. This seemingly isolated astronomical problem has since snowballed into a complex knot of fundamental questions, challenging the very bedrock of our cosmic understanding. We saw how this finding calls into question the standard hierarchical model of galaxy formation, which presupposed slow, gradual growth. To explain these early giants, scientists are now forced to rethink various aspects of physics and astrophysics. We discussed potential solutions. Perhaps the answer lies with the very first generation of stars, stars which might have been far more massive and efficient than we previously thought. Or maybe the solution involves massive seeds, black holes that didn't form from collapsing stars, but directly from the collapse of giant gas clouds, rapidly assembling galaxies around them. We also looked at more radical ideas. What if dark matter, the invisible scaffolding of the universe, possesses different properties than we assumed? Perhaps it is warm or self-interacting, which would fundamentally change the picture of how the first structures formed. Finally, we touched upon the boldest hypotheses. What if the very fabric of space-time, gravity itself, behaved differently under the extreme conditions of the early universe? Or perhaps we are simply miscalculating the mass of these distant galaxies, and our models, calibrated for nearby objects, simply fail when applied to these exotic systems. We currently lack a definitive answer. Each hypothesis has its strengths and weaknesses. Webb and other telescopes continue to gather the crucial data needed to help us decide. But one thing is already clear: our view of the early universe will never be the same. Webb has opened a new, unexpected window into the cosmic dawn, showing us that it was far brighter, faster, and more dramatic than we had ever imagined. This story is a perfect illustration of how science works. A single observation, one impossible piece of the puzzle, can trigger a chain reaction that forces us to rethink the entire framework. And in this pursuit of answers, in this constant dialogue between observation and theory, lies the great adventure of discovery. And so, our long journey to the dawn of the universe is drawing to a close. We've delved deep into the mystery of these impossible galaxies, and I hope you feel not just relaxed, but perhaps even a little dizzy from the sheer scale and complexity of the cosmos. The James Webb Space Telescope has certainly presented us with a puzzle, one that could spark a genuine revolution in cosmology. It showed us that the early universe was capable of creating gigantic, mature galaxies in record time, completely defying our long-held ideas about slow, gradual growth. This single observation has forced scientists worldwide to rethink everything, from the properties of the very first stars and the nature of the enigmatic dark matter, right down to the laws of gravity and the expansion history of our cosmos. We truly stand on the verge of a new era in astronomy. Perhaps the Standard Cosmological Model, which has served us faithfully for decades, is in serious need of a major update, or perhaps we are about to discover entirely new physical laws that were previously unknown to us. Whatever the answer may be, one thing is certain: the universe has proved to be far more surprising and unpredictable than we ever imagined. Thank you for spending this time with us, traveling together through space and time. If this lecture helped you relax, maybe even fall asleep, or if conversely it sparked your curiosity, please hit that subscribe button and like this video. It truly helps us keep creating new content. Now here is the main question for you. Which of the hypotheses explaining the impossible galaxy phenomenon do you find the most convincing? Is it due to exotic first-generation stars? Is strange dark matter to blame? Or are we truly on the verge of discovering a new form of gravity? Share your thoughts in the comments below. We'd love to read them. Good night and clear dreams of distant galaxies.